Hi guys, welcome back to Calculus. So our little adventure into random topics continues. Today you should kind of have most of your converge, diverge kind of things with series tests finished up, and we're going to move on to what that chapter was building toward, which is something very important infinite series known as a Taylor series. You were exposed to that in pre-calc a little bit. I called it polynomial approximations back then, and I just gave you formulas, but Taylor series will allow you to take any function, no matter what it is, and write it as an infinite series of just x to firsts and x to thirds, or maybe quantities like x minus 2's cubed minus x minus 2's to the fourth, but basically in polynomial kind of format. And you'd be surprised how useful that is, because a lot of things that you can't do with a function, you can do with a general function like sine or cosine or some e to the negative tan inverse or something like that. You can do maybe as a polynomial. So writing a function as a polynomial has its benefits, and something called analytic then, if it is a power series like this, power series could sound like it is, series with x's in it and things like that. And we're going to get to all that, but basically it's a more generalized version of something you already know, which is linear approximations. So we're going to start with that as a review, and we'll move on and build up like a degree at a time of what might be significant. Okay, so way back in the day, back when you were doing derivatives and applications of them, one of them was to find a linear approximation to a function. And if you remember what you do, basically to find a linear approximation, you're trying to find a tangent line around a function at a point. And around that point, I'm going to call that point the center. I'm going to use that term today as well. Around that point, the center, as long as you didn't stray too far from it on the tangent line estimated the actual function pretty darn well. Not perfectly. The farther away you go from the function, the more you go off on this line. But today we're going to find that maybe you could approximate with better than a linear, maybe a quadratic, maybe a cubic approximation, maybe a fourth degree or fifth degree or nth degree approximation. And the higher up in degree you try to approximate things with a curve, the better it gets. And actually, if you go to infinity, you have an infinite number of terms and an infinite degree polynomial, x to the first, x to the second, x to the third, x to the fourth, etc., all the way on to infinity, then the approximation gets so good to the actual function you want that it actually equals it pretty much everywhere. There's something called a radius of convergence, but you do not need to do that on your homework. It sometimes says find the radius of convergence in this section. You do not need to do that. We didn't have time for that. You'll pick it up. It's not that hard. If you got the converge, diverge things, then it's really not that hard to figure that out, but we'll get to that another time. Okay, so today we're going to find a linear approximation for x squared at 4. We're going to find a linear approximation for sine at pi over 4, and we're going to find a linear approximation for the square root of x around 16. In general, let's see, before we do all those things, let's just come up with a general formula, which might lead into today's lesson as well. In general, let's say you have any tangent line at some point x is c. So you're picking point C on the x-axis, and that's where your center is, and that's where you're trying to find a linear approximation around. What do you need to find a slope of a line, or to define any line? You need a point, okay, and you need the slope. So at that point, for this general function f of x, this derivative is f prime of x, at c would be f prime of c. So the slope at that point is f prime of c. It passes through what point? Well, I don't know. The x is c, we picked c, and the y is going to be whatever the function is at c. So the point is c, f of c, and the slope there is f prime of c. And if you might recall how we did this, we just went back to point slope form kind of stuff. So y minus y naught is m times x minus x naught. The y part of the coordinate is f of c, so y minus f of c is, the slope there is f prime of c, and then you have x minus the x coordinate of the point we have, which is c. And if you move the f of c to the other side, you solve for y. This right here is the equation for the tangent line right there. The tangent line is defined by y equals f of c plus f prime of c times the quantity x minus c. But remember, this tangent line is meant to approximate the function. So the function f of x is approximately equal to f of c plus f prime of c times x minus c, provided x doesn't stray too far away from c, from that center right there. So as long as you're not going too far off on your tangent line, it'll still approximate the function there very, very well. With this formula in hand, in fact, I want you to look at this formula structure because we're going to build on it. This is a linear approximation. There'll be quadratic terms next and cubics and so on and so forth. That's going to be a Taylor series that we're building up to. It's always going to start with something that looks very similar to this. Now, let's apply this to our actual problems. Number one today, we're trying to do x squared at the point C. We need the slope and the point. So let's see. Let's get the slope over with. Derivative, that's 2x, right? At 4, then the derivative would be 8, correct? Fair enough. F prime of 4 is 8. We also need the point. At 4, the function itself's y value is 16, so f of 4 is 16. Plugging things into this, f of x is approximately equal to f of c plus f prime of c x minus c. F of x was x squared, so x squared is approximately equal to the function at the thing I care about, which was 16, plus the slope there, which was 8, times x minus 4. So this is a good approximation for x squared, as long as we don't stray very far from the number 4. Same with sine on number 2. Derivative of that would be cosine. We need to find the value, the point and the slope. The point, well, what's the value of the function at the center I care about, which is pi over 4. It's sine of pi over 4, which is square root of 2. What's the derivative at that spot? Well, it's cosine of pi over 4, which is also square root of 2. So turn to my little handy formula here. The function, which is sine, is approximately equal to the value of the function at that point, square root of 2 over 2, plus the slope there, square root of 2 over 2, times the quantity x minus whatever we were centering it around, which is pi over 4. So there's my linear approximation for sine. So again, as long as I don't stray too far away from my center, pi over 4, this little linear approximation on the right is a very good estimate of what sine is around pi over 4. And same for the last one. If you had square root of x, number 3, then the derivative would be 1/2 x to the negative half, or 1 over 2 square root of x. The function at the center I care about, apparently I'm centering this around 16, is just the square root of 16, which is 4. So I have a point 16, 4. The derivative at 16 that I'm centering around is 1 over 2 times the square root of 16, alternative to an eighth. And if you plug in your little formula here for your linear approximation, the function, square root of x, is approximately equal to the value of the function at the center, 4, plus the slope there, which is an eighth, times the quantity x minus 16. So this linear thing on the right here is a very good approximation for square root of x, provided I don't stray too far away from 16. So today we're going to begin studying Taylor series, which I've already said is going to be same thing as polynomial approximations. Pre-calculating, we're going to see where those equations came from. We're going to come with an infinite degree polynomial that will approximate our function better and better. If I had a quadratic, it's going to be even a better approximation than a linear kind of tangent line. I have a cubic of best fit, maybe. But they're all going to be around the same thing. Like with the tangent line, you had a point you picked, and this point, we're going to approximate, quadratics and cubics around that point. We're going to call it the center, and we're going to build up that. Okay, so 8.1, the stuff over converge, diverge, and infinite series. That's due today. Hopefully you got through that. 8.2 is over this stuff Taylor series. It's very easy. The theory to build it up is complicated. So most of the lesson today will be kind of talking about why these things are what they are. But in the end formula for a Taylor series is very straightforward. On numbers 9 through 14, no interval of convergence. It says find the interval of convergence. You do not need to do that. It would not be that hard based on your knowledge that you just obtained from where things converge and diverge, but we'll save that for another class. You'll be okay on that. That's going to be due on Tuesday, the 28th, so let's get cracking. Chapter 8, infinite series. Last time we talked about all these tests here for whether infinite series does converge or diverge. This is the big stuff. This is, you've graduated from those Algebra 2 understandings of if the terms go down, then if the terms go to 0, then it converges. Not necessarily. That was a lie. But you have all these tests here to be able to check for different series and different cases whether it converges or diverges. Probably the ones you're going to use the most are kth term test. That's just to check if it's even possible to converge. So if the terms don't even go to 0, then you can just say it diverges and you're done. If the terms do go to 0, that doesn't mean it converges necessarily, but it could. And then you got to go, I say the integral test is pretty good. P series, if they come across something of this structure, that's a quick little test. But integral test is really good, and the P series test comes from this. You have a comparison test. If you have something really funky and you're not sure how to analyze it, maybe you can compare it to something simpler. And if you have a function on top and it converges, certainly the one that's less than it also converges. You have a simpler function on bottom and it diverges. And the more complicated function above it must diverge also. Same things we did with comparison tests with integrals back in the day. Alternating series test is pretty good for figuring things out. If you have something that's oscillating, plus minus, plus minus, plus minus, of course, it could start minus, plus, minus, plus. It really doesn't matter. The fact that it just changes sign back and forth forever is what matters. And then you have the ratio test and the root test. Probably those two are your babies. Those are you go to quite a bit, so you should put stars by those. You use a ratio test. So, hey, if you see a factorial, ratio test. If you see an exponential, like a 2 to the k or a 5 to the k or something like that, probably want to go to the root test. So, but every case is different. And it takes a lot of experience in doing problems, and that's kind of what the point of your homework was, is to get you exposed to, well, which one works here and which one doesn't work there. And they're tricky because we're going over them real quick, so hopefully you got through them okay. And if not, we can talk about them in the help session or something. Okay, section 8.7, still in chapter 8, is about Taylor series. Now, if you look down here, this is what we did back in first semester. A nice little linear approximation, a tangent line around some point on my curve. So around this point, as long as I don't stray too far away from that point on this tangent line, it's still a pretty good approximation for what the actual curve is. But could we do better? Well, in this figure right here, we have this exponential, still e to the x, and you see this weird polynomial right here, 1 plus x, which was the same as this one was, with a little extra term added on, a quadratic term. Now, this blue line here seems to fit around where x is 0 even better than this one. The blue line here, the tangent line, it kind of diverged from the actual function pretty quickly as you went away from it on either side. But this one, if you go along the blue curve, it takes a while for it to start diverging and getting farther away from the actual function. You see it, this right in here is even more closely fit to the actual function in red than the tangent line was. So this linear approximation is good. This quadratic expression is even better. And we can keep generalizing this. Over here in this picture, you got a nice graph of this black line. It looks like sine, it is, okay? Could you approximate sine? Yes, you could. Here's the red line. This would be the tangent line. We're doing this around 0, by the way, so approximating sine around 0. And you see the tangent line there. The red line is pretty good as long as you don't go too far away. Now, there is no quadratic one for this, but there is a cubic. If you look at this kind of orange line, and it comes in, and it kind of hugs it, and it leaves, man, that's an even better fit for sine around there. This yellow one is a 5th degree polynomial, and it's an even better approximation. As you keep going out farther and farther, you see that these are odd degrees. I wonder why they're odd degree polynomials approximating sine, which is an odd function. But as you go out farther and farther with higher and higher degrees, you see that even way out here, like the purple one or something like that, man, it's fitting sine really, really well around there. Of course, eventually it falls apart and that diverges. But I guarantee you, if you just get better and better and higher degree approximations, how far away you can stray from the center in either direction has to have a good approximation will get better and better and better. And that's what we're going to start talking about today. So finding all these curves here is our task. How we're going to do that, that's going to be quite a little thing. Okay, well, let's see here. Why a linear approximation works around a specific point is because that point of the function and that point on the tangent line are the same. That's what we really want. When you're trying to find a tangent line or a linear approximation, the point is a point on the graph, right? And you want the slope of your tangent line to be the slope of the function at that point. That's the point. So their 0th degree approximations match. What's a 0th degree? It's just a constant, which means their points match, okay? So they actually have the same y-coordinate, right? The y-coordinate on the graph is the same as the y-coordinate of the tangent line. And they have the same also 1st degree approximations. The slope of that tangent line is by definition the slope of that point right there. So the point they share a point in common. The actual function and the linear approximation share a point in common. That's the 0th degree approximation. They also share the same slope. That's the 1st degree approximation. If I wanted to have a 2nd degree approximation, I would want to follow that same logic. I would want their second derivatives to also match. If I want a 3rd degree approximation, a cubic approximation, I would want the 3rd derivative of my cubic at that point to be the same as the 3rd derivative of my function at that point. I would also want the 4th derivative of my function to match the 4th derivative of my polynomial approximation, and so on and so forth. I would want the 77th degree approximation, 77th degree polynomial, I would want the 77th derivative of that at the point to match the 77th derivative of my function at that point. So we want our approximation and our function to match with all their derivatives. If they have the same points, if they have the same slope, if they have the same concavity, if they have the same jerk, if they have the same, if you keep going down on the derivatives, if they have the same structure down at the bottom level, then it turns out that they are going to match better and better and better. And that's the cute thing right there. Okay, so we're going to figure out, well, okay, how do I do a quadratic approximation? How do I do a third degree approximation? Well, here we go. Let's dive in with this thing. So first off, we are going to assume that our function can be approximated by something that looks like this right here. Okay, now these first two terms, all these a's are just constants, by the way. Okay? And the first two you should kind of recognize from the warm-up. This first two are just the linear approximation. Here's the value of the function at c. Here's the slope of the function at c times x minus c. But we'd like to go higher. Now, since this is all centered around some point c, all of our approximations are involving x minus c as the exponent thing. So quadratic approximation, if I want to have three of these, I can have a quadratic approximation. I have some number times x minus c squared. If I want a cubic approximation, I could add on another number times x minus c cubed, and so on and so forth to whatever n degree approximation I want to use. All right, well, we said all their derivatives have to match. So here we go. Let's just take a bunch of derivatives and start looking for some patterns, okay? So the 0th degree approximation, we said, is just this given by this equation right here, okay? So we're assuming it's something like this. We want all their derivatives to match, so we got to take all these things derivatives. So let's see. Well, take the derivative of our function. We want the first derivative at x, being c, to, well, be the first derivative of this thing. Well, what's the derivative of this big old thing up here? Well, let's do some calculus. This is a constant, so its derivative is 0. This is a1 times some x stuff. Derivative of x stuff is just 1, so it's just a1. The derivative of this, the 2 comes down. You got 2a2 times x minus c to the first. And you got 3 coming down. You got 3a3 times x minus c to the second, and so on and so forth. So take the derivative of this top one. Obviously, you get the first derivative. Well, take the derivative again. The second derivative would be, and then this one, there's a constant, so it's gone. The derivative of this one is just a linear, so that goes as 1, and you got 2a2. Then the 2 comes down, you got 3 times 2 times a3. This one, the 3 would come down, you got 4 times 3 times a4, etc., 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 all the way to the end. And you keep doing this for indefinitely forever. Take a derivative of that, take a derivative of that, take a derivative of that. In general, you're going to find that the nth derivative of any function goes all the way down to this kind of last term right here. In fact, if you see the first derivative, it starts with an a1. The second derivative starts with an a2. And every time you do this, the first term goes away because it's a constant, and you have one less term to deal with. If you go all the way down to the nth derivative, and you kept taking derivatives of this last term right here, so the nth power, right, well, there'd be an n coming down, there'd be an n minus 1 coming down, an n minus 2 coming down, n minus 3. And all these last ones at the nth derivative would go away. Besides that, you'd be left with this n times n minus 1 times n minus 2 times n minus 3 times all the way down to 1 times an. Okay, well, what can we do with that? Let's see here. Well, we're trying to make sure they match at c. So I'm going to plug in c into all these things. And the nth derivative at c is given by the same exact expression. In fact, if you look at the 0th derivative of c, what happens? Well, c minus c is 0. C minus this c squared is 0. C minus this c cubed is 0, etc., etc. All these terms go away except for the first one. The 0th derivative at my point is what a0 is going to be. The first derivative at my point is going to be what a1 is. The second derivative of my function at the point I care about is going to be 2 times what a2 is. The third derivative of my point is going to be 3 times 2 times a2. The fourth derivative is going to be 4 times 3 times 2 times a2. And in general, like I just said, this is the master equation for it for any nth derivative. Okay, so if we kind of equate things, like I was just saying, the 0th derivative of my point must be a naught. The first derivative of my point must be a1. The second derivative must be 2a2, etc., etc., etc. And in general, at any point c, this is the equation we have right here. If you solve for this coefficient, remember we're trying to write a long polynomial with coefficients a naught, a1, a2, a3. So we want to know what those a things are. What is a4? What is a5? How am I going to find it? Well, according to this equation right here, the nth coefficient in your series is going times all this n junk should equal the nth derivative of the function I care about at the point. So solving for all these coefficients, a naught is just going to be the 0th derivative of the function at c. And I'm going to write it to show a pattern divided by 1. 1 is the same thing as 0 factorial. That's why 0 factorial is divided as 1, by the way, so this pattern works out. A1 is going to be the first derivative of my function over 1 factorial. A2 is going to be the second derivative of my function over 2 factorial. Because you see on the bottom here, you're multiplying by things over and over again. 4 times 3 times 2 is 1. That's 4 factorial. 3 times 2 times 1 is 3 factorial. In fact, way down here, even for the nth term, if you solve for that, any term, the nth coefficient, I should say, is the nth derivative at my center divided by n times n minus 1 times n minus 2 times n minus 3, and they keep going all the way down to 1, which is known as n factorial. Now, this is very powerful. And if you didn't follow all that, that's okay. But the key thing is that the coefficient, the nth coefficient in my polynomial approximation should exactly equal the nth derivative of my function at the point I care about divided by n factorial. So if you go back and you rewrite everything in terms of, remember our polynomial approximation was something that looked like this right here, correct? This is what I am guessing that the polynomial approximation should look like. If you plug in what a naught is and a1 is and a2 is that we just figured out so that all their nth derivatives match, then it turns out that the series looks like this right here. And this is known as an nth degree Taylor series right here. And every time you add on a term, this is a 0th degree approximation. These two together here would be a 1st degree polynomial approximation, i.e. a linear approximation that you already did. These 3 here would be a quadratic. These 4 would be a cubic, and so on and so forth. And we can write this big long pattern in a compact format like this. And it's saying that f of x is approximately equal to the sum from k equals 0 to infinity of the kth derivative at the center divided by k factorial times x minus c to the k. In fact, if the series goes on and on forever and ever and ever, these two will not only approximate each other, they will equate to each other. And that leads us to the final thing, which is called a Taylor series. So there's a lot of theory to build up. And if you didn't follow all of it, don't stress out. What you really need to do is write down these two definitions. I always like to show where things come from, but if you don't completely understand where they come from, I hope you at least understand the idea that these are polynomial approximations. Just same thing you do with linear. We're just going to do higher degrees. Cubics, 4th degrees, 5th degrees. In fact, we're going to go to an infinite degree polynomial. And the more terms you add on to an infinite series, the better this thing's approximated. And as the number of terms goes to infinity, this series over here actually equals the function. There are 2 kinds of series. Actually, there's only one. The main title you want is the Taylor series. Okay, this is the Taylor series. The center, the point you're doing this around, is C. So all you got to do is write down this equation, and what's buried inside this equation that you have to find? You can find factorials pretty darn easy. You can write x minus something to a power very easily. Essentially, all you got to do to find Taylor series is find the derivative, repeated derivatives, first derivative, second derivative, third derivative, at the point you care about, C, the center. And that's the very general thing. And I'd like you to learn that term Taylor series. Quite often, if a function is defined at 0, 0 is a convenient thing. Why would you want to have x minus 7 to a power when you could just have x to a power? So centering things around 0 is very common. A special case of the Taylor series is known as a Maclaurin series. And all it is just a Taylor series with the center being a specific number, 0. So if you plug 0 into this equation for a Taylor series, you get out this Maclaurin series. And that's all there is to it, okay? So you should know both those terms. People do Maclaurin series probably more often than Taylor series because this is nice and compact. Plugging in 0 to things is usually pretty easy, and you just have extra powers. But in general, you could center around any point you wanted, and that's what Taylor series are for. So most of our problems, it doesn't matter what point you pick, but I'll specify some and you can do it. Now, here's 4 examples for you today, 5 in fact. First 4 ask you to find the Maclaurin series. Now, that just means what? It's a Taylor series, but I'm just saying the center is 0. Number 5, I'm doing a different center on you. I say, oh, I want you to approximate this function centered around 2. And so you do, no matter, it's the same process no matter which one you're doing. It's just what you're plugging in for your center and for your derivatives. So let's see. In pre-calc, I gave you a worksheet, that's a handout that said polynomial approximations. And on 3 of them were e to the x, sine x, and cosine x. And now we're going to see where they come from. Those polynomial approximations were just the Taylor series, and we're going to figure them out from scratch. So here's our example. Number 1, the Maclaurin series for e to the x. So here's our equation for the Taylor series right here. Like I said, in order to do these, you just basically need to compute a bunch of derivatives at the point we care about, our center. For Maclaurin series, by definition, when they say Maclaurin, it's automatically the center is 0. So before I even dive in and start doing all this fancy stuff, let's just find a bunch of derivatives. That's your first. All right, what's the 0th derivative of e to the x? I didn't take a derivative, so it's e to the x. The first derivative of e to the x is e to the x. In fact, no matter how many times you take the derivative of e to the x, derivative is e to the x. So the kth derivative of my function is e to the x. I need to know in this Taylor series equation what the kth derivative, any derivative, is at the value I'm centering around, which is 0. So what's the 0th derivative at 0? Well, e to the 0 is 1. And in fact, any derivative, since it's e to the x, any of the derivatives when you plug in 0 will be 1. So what's a way to write this? Well, I can put it in a compact format right now, or I'll show you the pattern again. Here's the pattern. Taylor series is the 0th derivative at my center, which is 0 over 0 factorial, plus the first derivative at my center, which is 0 divided by 1 factorial, times x minus 0 to the first, or just x, plus second derivative of my function at 0 over 2 factorial over x minus 0, or just x squared, and so on and so forth. And if you plug in what the derivatives are, well, this is 1, this is 1, this is 1, this is 1, you get 1 over 0 factorial plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 2 factorial x to the third. And as a nice, concise way to write that, and you should try to write it in sigma notation if you can, e to the x is just the sum from k equals 0 to infinity of x to k over k factorial. And if you don't want to write out like this first and you do see a pattern, fine, just plug it into this thing right here. In fact, you could just plug it into this formula right off the bat. Because what's the derivative at 0 for anything? It's 1. So it's the sum from k equals 0 to infinity of 1 over k factorial times x minus 0, which is just x, to the k. I can put the x to the k on top, you can. So e to the x is the summation from k equals 0 to infinity of x to the k over k factorial. That will converge everywhere. So if you write out more and more of these terms, it'll better and better and better approximate e to the x around, what point are we doing? Around Maclaurin series, around 0. So you would see if you did, when k is 0 and plugged it in and then just did that, okay, be a really terrible approximation for e to the x, be okay. K equals 0 and k equals 1 added together, be a linear approximation. K equals 0 and k equals 1 and k equals 2, all of them together, it'd be a quadratic approximation of e to the x around there, which is what you had in the warm-up, or not in the warm-up, but on the first slide, they said, okay, here's approximation for e to the x. And if you just kept doing that, you would get the same exact graph they had on that thing for the quadratic. But of course, you go on purpose and infinite. Okay, how about the Maclaurin series for sine of x? Well, again, it's the same process over and over again. I need to take derivatives over and over and over again. Let's see. Well, 0th derivative of sine, derivative of sine's cosine, derivative of cosine's negative sine, derivative of negative sine's negative cosine, and derivative of that is sine, and you're back to where you started. Remember, these repeat every 4. So these would keep repeating every 4 indefinitely. And that's good. It's good when you can see a pattern because you have to write out an infinite number of these things. So if you see a pattern in them, you can write it more compactly. Well, again, we're trying to find the Maclaurin series. So I care about what these derivatives are at 0. So let's plug in 0 into each of them. The 0th derivative at 0 would be just sine of 0, which is 0. The first derivative at 0 would be cosine of 0, which is 1. The second derivative at 0 would be negative sine of 0, which is 0 again. And the third derivative of negative cosine at 0 would be negative 1. And then the pattern starts all over again. So it's going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1. In general, in case you want to get all fancy, by the way, whenever you take a derivative of something, you add a pi k to it inside the trig function. I know for sine and cosine. So that's a cute little trick I use a lot of times. So if I want to find the kth derivative of sine, I basically inside of this add how many pi over 2's, k of them, so plus pi k over 2. That's a cute little trick that you might want to learn. Or for cosine too, that works also. but in general, that's what's going to be. So now back to our thing. Let's plug it in here. Let's see what this thing looks like. This is our pattern, correct? We're doing it 0. The 0th derivative at 0 was what? 0? Yeah, so there's going to start with a 0 over 0 factorial. The first derivative at 0 was 1, right? And so it's 1 over 1 factorial times x. Second derivative at 0 was 0 again. Third derivative at 0 was -1. And then it keeps repeating, correct? Every 4 it repeats. So let's see what we have here. Well, this is just 0. 0 divided by 1, 0 factorial is 1, is 0. So there is no constant term. There's an x over 1 factorial. There is no quadratic term. There's a negative x cubed over 3 factorial. And if you kept doing this pattern out, it would look something like this. X over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Interesting. And how would I write that in sigma notation? It's going to be ugly. Well, let's look at the exponents. They go 1, 3, 5, 7. So do the factorials on bottom, 1, 3, 5, 7. So they go up by 2s, and they kind of start at 1. So I'm thinking on the bottom, maybe a 2k plus 1 factorial. Does that make sense? Try it. When k is 0, what do you get? 2 times 0 is 0, plus 1 is 1. You got a 1 factorial start. When k is 1, you'd get 3 factorial. When k is 2, you get 5 factorial. So great, the bottom is going like I want. And since the bottom is based on 2k plus 1, and the exponents are the same thing too, they're like a 1 and a 3 and a 5 and a 7, maybe I could have x to the 2k plus 1 as the exponent. But it also oscillates. It's plus, then it's minus. Plus, then it's minus. So I'm going to throw in this little -1 to the k. The first term should be positive. Is it when k is 0? Yes, because when I plug in 0, anything to 0 power is positive 1. And when k is 1, -1 to the first would be a negative. So this will go plus, minus, plus, minus, plus, minus forever. And you kind of have it written in this compact format here. If you are having trouble writing it back in sigma notation like this one, I will accept this answer right here where you show the pattern written out for a bunch of terms plus ... I know writing a random series with a pattern in sigma notation is not one of our strong suits, but I encourage you to try. So it's always nice to have it written as a compact format like this because this does represent it going on forever, and the same thing as this one. What about cosine? Very similar proof. I'm going to take all the derivatives of cosine over and over again. They do repeat every 4. Again, you're trying to find the Maclaurin series. That means your center is c equals 0. So you want to find these derivatives at, trying to find all the derivatives at your center, so at 0. And in this case, the pattern is going to go 1, 0, -1, 0, 1, 0, -1, 0, and so on and so forth forever. Same kind of trick I could say for this, just adding pi over 2 every time you take a derivative. You add pi over 2 to your function. I mean, check it. I mean, what's the sine? It's cosine. Well, you took one derivative. Guess what sine of x plus pi over 2 is? If you go do some trick identities, it's cosine. But again, you just plug in your little formula right down here. The 0th derivative this time is 1. The first derivative this time is 0. The second derivative this time is -1. The third derivative is 0. So you get this pattern out. This time it's 1 over 0 factorial minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th, etc., etc. Now this one, if I want to try and write compactly again in sigma notation, what's going on the bottoms? Well, it's 0, 2, 4, 6. It's going up by 2s. Okay, so I'm going like a negative 2k something. It starts at 0. So maybe a 2k plus 0, which is pointless. Just write 2k. So on the bottom, how about just 2k factorial? Let's see if that works. When k is 0, we get 0 factorial. Cool. When k is 1, we get 2 factorial. Good. K is 2, we get 4 factorial. Great. And since the bottom exponents are going up by 2, 0, 2, 4, 6, look at the exponents. 1 is just x to the 0. Then you got an x squared, x to the 4th, x to the 6th. The exponents are going up in the same way. So the x is going to be raised to the 2k again. And again, it oscillates from plus, minus, plus, minus. So this -1 to the k is there to compensate for that. You might recall that sine is an odd function. You remember what odd function means? It means it's symmetric across the origin. There's a reason they call those odd and even functions. If you go back to sine, look how sine can be written in terms of only odd exponents. Sine is an odd function because if you go down and look inside of it, it's built off of only odd degree powers of x. Cosine is the same on both sides. It's even. We call something even for a good reason, because if you go down and look inside its polynomial approximation, it's only made out of even powers right there. So you can tell what's going to go on in a graph too, by the way. If it's only constructed with even exponents like this one is, cosine, it's going to be an even function and the same on both sides. If your series representation is only built off of odd exponents, then it's going to be an odd function. And if you see something like the e to the x, which has a mix of them, oh, it's got odd and even. Well, is it either one only then? No. This one would not be even nor odd. It has no symmetries about it. So you can tell a lot by just looking at the polynomial approximation. All right, now this one's cute. It could be any function. So let's try x plus 1 cubed. And the Maclaurin series, so we're centering around 0 again. So here we go. First step, I need all these derivatives. So let's start taking derivatives. My function is x plus 1 to the third. The first derivative will bring the 3 down, x plus 1 to the second. Chain rule, there's nothing inside. Derivative inside is 1 every time. Second derivative, bring the 2 down. You got 3 times 2, which is 6, times x plus 1 to the first. Take the third derivative. Well, that's just 6. Take the fourth derivative, you got 0. Fifth derivative is 0. Is it possible this thing just terminates and doesn't go on forever as a polynomial approximation? Yeah, it is. In fact, I think for this cubic function, probably the highest degree approximation we're going to get is a cubic. Makes sense. I mean, how can I use a fourth degree to approximate a cubic? Doesn't make sense. But again, we're trying to find the Maclaurin series, so we're centering this around 0. So plugging in 0 in for all these for the center. 0 plus 1 cubed would be 1. 3 times 0. In fact, whenever you plug 0 into this expression, it's just 1, right? And you raise it to a power, who really cares what it is? So it's just kind of the numbers in front. The derivative, 0th derivative is 1, first derivative is 3, second derivative is 6, the third derivative, no matter what I plug in, is 6. And for the fourth and fifth and stuff, no matter what I plug in, I get out a bunch of zeros. So let's see what we get here. X plus 1 cubed is, well, here we go, 0th derivative at my center is 1, so 1 over 0 factorial. Plus the first derivative of my function at my center 0 over 1 factorial, that would be 3 over 1 factorial times x. Plus the second derivative at 0 over 2 factorial, well, that's 6 over 2 factorial times x squared. And you know why these are just x's here, right? Because, the center is 0. This is really x minus 0 to the first. This is really x minus 0 to the second. This is really x minus 0 to the third. But we can drop the minus zeros like we always do. And so on and so forth. And then eventually, after the third derivative, you plug in 6, right? And it's third derivative over 3 factorial times x to the third. But the fourth derivative on are a bunch of zeros. So even if you go on forever, 0 divided by anything or 0 times something is still 0. So these after here don't even matter. These first 4 terms are the only ones I'm going to need. And if I clean them up, 6 over 3 factorial is 6. 6 over 6 is 1. I get x cubed. 6 over 2 factorial. 2 factorial is 2. 6 over 2 would be 3. So I got 3x squared. I'm writing the normal way now with the leading term being the highest power. You got 3x, you got 1, and you have this expression right here. So x plus 1 cubed approximated around 0 is given by this little polynomial right here. And you might recognize that. That's something from Pascal's triangle. If you took x plus 1 cubed, you got the 1, 3, 3, 1 right there. And you can think of the binomial expansion of this as a third degree Taylor series approximation for x plus 1. In fact, they're identical. And you know that, right? You know x plus 1 cubed, if you went and did the Pascal's triangle, would actually exactly equal to this thing, and they are equivalent. This is an approximation centered more around like -1, because I see this as like x minus -1. This would be an approximation for x, centered around -1, but this one over here is centered around 0, so they have different centers, and that's kind of cute. Okay, let's actually do it as a Taylor series, though. Those were Taylor series, but we were always plugging in 0. Let's do something a little bit more interesting this time. Let's try to go the other way. Let's say I just gave you this cubic, x to the third. Now again, what's probably the highest degree approximation I can have for this no matter what I do? It's probably going to be a third degree. But we're going to center this one at 2 this time. So we're going to do the same thing, but we're going to plug it in 2 for where I care about. But same logic. We need to know all the derivatives. So here we go. X cubed is the 0th derivative, obviously. First derivative is 3x squared. Second derivative is 6x. Third derivative is 6. And then they go down to zeros very much like the last one did. Plugging in 2. Let's see, if I plug it, what's the 0th derivative of my function at 2? What's the function at 2, which is just 2 cubed or 8? What's the first derivative at 2? It's 2 squared 4 times 3, which is 12. What's the second derivative at my center 2? 6 times 2 is 12. Third derivative is 6. Fourth on is 0. So going back to my approximation, f of x is the zeroth derivative at, ooh, that's an error on my slides. Copy paste. Shame on me. What should this say? It should not say the zeroth derivative at 0. What should it say? The zeroth derivative at 2 over 0 factorial plus the first derivative at 2 over 1 factorial. I'll fix this on the PDF and upload it in case you want that. The second derivative at 2, not 0, over 2 factorial. Oh my gosh, this is terrible. It's just so bad, I gotta fix this. This is so bad. So bad. So bad. I'm gonna fix this right now. This is just terrible. I apologize, everybody. Because this should be what? X minus 2. And if I'm centering around 2, all my stuff should have x minus 2's in them. That was terrible. 2 here. This is now x. Let's copy this. Yeah. There we go. That's going to be a lot better. My apologies on that. So let's look at it fresh now. This should make more sense. This matches this pattern exactly, and I'm centering at 2. This is what happens when you copy and paste. In the last 4 examples, we're all centering at 0. But anyway, the zeroth derivative 2 over 0 factorial plus the first derivative 2 over 1 factorial times x minus 2 to the first plus the second derivative, etc., etc., etc. Plugging things in, the zeroth derivative at 2, we said was 8, so it starts off with 8 over 0 factorial. The first derivative at 2 was 12, so it's 12 over 1 factorial times x minus 2 to the first, plus the second derivative at 2, which is 12 over 2 factorial times x minus 2 to the second, and then so on and so forth. And since your derivatives eventually go to 0, this pattern does stop. After you get past the cubic term, this no longer has any value. And if you clean all this up and simplify the factorials and determine the coefficients, it looks like I'm going to write them in the traditional order. X minus 3 is the same thing as x minus 2 cubed plus 2 times x minus 2 squared plus 12 times x minus 2 plus 8. We've written a cubic centered around 0 as a cubic centered around 2, which is kind of cute right there. But I think you see that these are very straightforward. It's just tedious. Essentially, what do you got to do? You have to find repeated derivatives over and over and over again until they either go to 0 or till you can see a pattern in them. And then you're plugging in whatever your center is. So if your center is 2, plug in 2, figure out the derivatives, all the derivatives at 2. Your center was 29, plug in 29 and all the derivatives and see what you get. And then you just put it in this little format right here and simplify things if you can. If it goes on forever, try to look for patterns and show me what the pattern is that goes on forever. A lot of them don't have patterns. A lot of them, if you found like tan, and think about what tan's derivatives do. They get so gross and so ugly so fast. Tan is what? Secant squared. Sure, that would be 2 secant squared tan, then you got a product rule, and you got more product rule. They're going to get gross real fast. So taking the derivatives is probably going to be what's the gross part of this stuff, and plugging in the points into the derivatives. But once you got that, you just plug them into the little formula here. Make sure it's x minus your center every time. If your Maclaurin series, your center is 0. If it's a general Taylor series, your center could be anything. They could say 2, 4, whatever. In this example, it was 2. And that's kind of all you got to do for that. So there is that. Now here's a freebie from your homework. Okay, this is number 11. This is always a tricky one, so I like to do this one right here. Find the Taylor series about the center E for natural log x. So again, Taylor series, not a Maclaurin series because the center is not 0. The center is E, but nonetheless the pattern is the same. So what do I got to do? I got to start taking derivatives. Here we go. Zeroth derivative of this would be natural log of x. Cool. The first derivative of that would be 1 over x, or x to the negative first. Second derivative, bring the exponent down, -1, x to the 1 less, next to negative second. Third derivative, bring the -2 down. Now the negative times the negative is a positive, and I have 1 times 2. We'll leave it like that because there's a pattern coming up. X to the negative third. Take the derivative of that, -3 comes down, now it's negative, 1 times 2 times 3, x to the negative fourth. Take the derivative of that, -4 comes down, now it's positive, 1 times 2 times 3 times 4, x to the negative fifth. Derivative of that, up, negative, up. And in general, it seems like there's a pattern to these derivatives right here. First of all, the first one's kind of funky. It's natural log of x. Let's just leave that one alone. But all the ones with the x's definitely have a pattern. The first derivative is involving x to the negative first. Second derivative is involving x to the negative second. Third is x to the negative third, and so on and so forth. And they do kind of oscillate. The first one is a positive, then the second one's a negative, then a positive and a negative, and a positive and a negative. So how can I write that oscillation in general if I wanted to write an equation for the kth derivative? Well, let's just check it. The first derivative should be positive. So when I plug in 1 for k, I should get out a positive. So I'm not going to write -1 to the k, because that would be what? When k is 1, that would give me a negative. I don't want that. I want a positive. So I'll offset it. I'll add a 1 to the -1 power, and then will that take care of the oscillation? Well, let's see. When k is 1, I got -1 to the second, which is a positive, and that should be positive. When k is 2, I should get a negative out. When I plug in 2, 2 plus 1 is 3, -1 cubed is -1. So this part takes care of the oscillation. Like we said, the exponent for the x is just going to be negative whatever the derivative is. So the kth derivative is going to be x to negative k. And what's in front of all these things? It looks like a factorial, but not quite the exponent. The sixth derivative doesn't have a 6 factorial. It has like a 1 less than that, 5 factorial. The fifth derivative doesn't have a 5 factorial. It has like more of a 4 factorial. So you have 1 less of a factorial in this. So if you take the kth derivative, basically there's going to be a k minus 1 factorial. You always wonder why this factorial thing was made up anyway. This is why. This is why factorials are here for. Because if you do repeated differentiation over and over again, the exponents keep coming down. Myself, this is exactly why you have it. It's in the Taylor series. It's in the natural log thing too. Okay, now you're trying to do this at e, so I need to go plug in e into all these derivatives. Now the 0th one, that's kind of off by itself. It's a freak one. If you plug in e, well, what's the natural log of e? It is 1, right? Okay, cool. This one, when you plug in e, you get e negative first. This one, you get -1 factorial times e negative second, 2 factorial. And in fact, in general, as you go down, since we already have an equation for the kth derivative, plugging in e, the kth derivative e is just going to be -1 to the k plus 1 times k minus 1 factorial times e to the negative k. That is the equation for the kth derivative of e. So I did it again on this slide. Shame on me. Copy paste is a dangerous, dangerous thing. You will want to find all these centered around e, correct? So you should have a bunch of x minus e's floating around. Whoops. E, this one, that one, this one. Okay, I'm back. Okay, so on this one, again, matching this up, it's the 0th derivative at e times 0 times x minus e to the 0. X minus e to the 0 is nothing. Who cares about that? First derivative e over 1 factorial times x minus e to the first. Second derivative at e over 2 factorial times x minus e to the second, and so on and so forth. Well, let's start plugging in things we have in our pattern and see what's going on here. First of all, the function is natural log of x, right? What's the 0th derivative? E, we said it was 1, so it's going to start off with a 1 over 0 factorial. The first derivative e was what? Just e to the negative first, correct? So e to the negative first over 1 factorial times x minus e to the first. Second derivative, well, we had an e to the negative second times a -1 factorial over 2 factorial times x minus e squared. Third derivative was 2 factorial e to the negative third. That needs to be divided by the 3 factorial and times x minus e to the third, and so on and so forth. But look at this. This is so cute. Remember last section when we were talking about how you can simplify factorials and stuff like that? What's 2 factorial over 3 factorial, for example? What is 3 factorial? It's 3 times 2 factorial. So if I write this right here as on the bottom, 3 times 2 factorial, the 2 factorials cancel. It's just a 3 on bottom. This one right here, 4 factorial is 3 factorial times 4. So if I write this as 4 times 3 factorial, the 3 factorials cancel. I'm just left with a lone 4 on here. In fact, that's going to happen all the way through. Basically, the factorial on the top is going to cancel with most of the factorial on the bottom and just leave the number that it started with. So let's try to summarize all this up. Here we go. Natural log of x is 1 plus e to the negative first over 1 factorial doesn't really matter, x minus e minus, again, remember the factorials kind of cancel, just leave the number on the bottom. So it's e squared, e to the negative second over 2 times x minus e squared plus this one we said there's just a 3 left on bottom, e cubed, e to the negative third over 3 times x minus 3 to the third, minus, and so on and so forth. Could I write this? Oh man, that 4 factorial doesn't need to be a factorial. So, man, my slides are off today. I apologize to everybody because you simplified it. So what am I doing? Silly man. Oh, there we go. So it's just over the number basically in the end. So how can I write this compactly? Well, let's see. It's just the number on the bottom, correct? For the first derivative, it's 1. For the second derivative, it's 2. For the second derivative, so basically on the bottom, I can just write k. I'm gonna ignore this 1 off to the side for a second. You'll see why in a minute. I'm gonna do the rest of this pattern. This one started off as e to the negative first when k is 1. When k is 2, it's this. When k is 3, is this. So you can see pretty easily that this is, when you plug in the pattern right here, this is what you'd get for the compact terms for all these. Why can I not just lump the first term in with this and say, hey, it goes k equals 0 to infinity? Well, when k is 0, what's wrong with plugging that into this pattern? You'd be dividing by 0, which is not correct. So the first guy, the 0th derivative, he's kind of special because in the pattern, he kind of breaks the pattern. The first one's just a natural log of x, and the rest are all x to negative exponents and things like that, have a definite pattern to them. But so that's why that one's kind of off by itself. You got a 1 plus this infinite series. But essentially, no matter how complicated it gets, follow this formula, okay? Write it out term by term like you need to. When k is 0, plug in 0, write that very first thing. When k is 1, plug in 1 into all this, write the second thing. K is 2, plug in k is 2 for this, and then write out the third thing. So as long as you got all the derivatives evaluated at your center, and you can painstakingly plug them into this equation one by one by one, hopefully you'll see a pattern. This is one I did for you because to see it, the factorials in this pattern and to know that it cancels out with the other factorial on the bottom for the Taylor series is probably something you guys get stuck on. So I decided to just do this one for you. But this is your answer for number 11. 1 plus the summation from k equals 1 to infinity of negative 1 to the k plus 1, e to the negative k over k, all times x minus e to the k. So that's how you do Taylor series. It's an exercise in tedium, really, taking derivatives so many times and plugging in your center and then writing the formula out. I do encourage you maybe write out the formula if you can't see how things are going to cancel out, especially if you see factorials in the pattern. Simplify things as much as you can. Your calculator does this too, so you might want to check it. If I don't think 83s do, but if you've got like an 89 or one of those fancy computer-aided ones, there might be something that says Taylor, and it could spit out the Taylor series for something for you. But you need to show your work. You need to show you took all the derivatives. You need to show that you did all this stuff to do it by hand. And then it's one of those things that after you do it by hand for a billion times, sure, let your calculator do it. You know what the Taylor series entails, but that's basically all there is to it. So I'll shut up now. You got your homework over convergence and divergence due today. You have this stuff over Taylor series due on Tuesday. It's not that many problems, really, but they are kind of tedious and take a little bit of time. So good luck on that, guys. I will touch base with you. We're getting close to the end. Next time, I believe we're going to do a little Diffie Q, some basics, so that's going to be good. Have a great weekend, and I'll talk to you later.